Right, let's get to that last example. Says the radius of a sphere is 6 centimeters with possible error 0.01 centimeters. Find the maximum possible error of the volume. Okay, so kind of think, maybe some kind of factory is producing a sphere, producing a bunch of these, and they know that their machinery might be off by a little bit in the radius. So the radius of that sphere might be off by as much as 0.01 centimeters. How would that affect the volume, right? If you're off in the radius, if you make your radius too big, that's definitely going to put too much volume into the sphere. But, there's kind of like tolerances for what's acceptable and what isn't. So if there's a maximum possible error of 0.01 centimeters, what would that tell us about the maximum possible error in the volume? How far away would that volume be from what the volume was supposed to be? Turns out differentials are a great way to find that out. So here we go. Radius of a sphere is 6 centimeters, a possible error 0.01 centimeters. Find the maximum possible error in the volume. Okay, so what we need to begin is a function. We want to know the error of the volume. So what is the volume of a sphere? That is the function we want. Maybe it's been a little while since you thought about the volume of a sphere, but that's something we could look up, right? It turns out it's 4/3 pi r cubed. So what we're going to do with v equals 4/3 pi r cubed, we're going to take the differential of both sides. And I can say dv equals, our other variable over here is the r. So we're going to, right, the 4/3 pi is all a constant. So we can multiply the 3 down, give us 4 pi r squared dr. Now, what do all of these things represent? So I know that the radius is the radius. I know the volume is the volume, but what is dv and what is dr and all this? dv, that's how much the volume might be off by compared to the ideal. This is the volume error. How much possible error is in the volume? That's simply dv. The same way, dr is our radius error. How much might the radius be off by compared to what it's supposed to be? What is r? Well, I guess you could say it's the radius, but I think it'd be more accurate, or maybe more precise, to say this is the ideal radius. What are we aiming for? Okay. So what are we going to do? Well, we know what the ideal radius is. It's 6. We know it has a possible error of 0.01. That's dr, 0.01. So if we plug those in, we can find the maximum possible error in the volume. dv equals 4 pi times 6 squared times 0.01. I think this question said to round to 2 decimal places, so let's do that. 4 pi times 6 squared times 0.01, and I got 4.52 when I round. So there you go. Now, kind of reflecting on this, what would be the units? Maybe let's start with that. What would be the units on our dv? So it turns out the units for dv are the same as the units for volume. So in this case, that's centimeters cubed. Our volume might be off by as much as 4.52 centimeters cubed. What else could we reflect on? It turns out we don't need calculus to get this answer, but it turns out it's quite a bit faster. If we knew that this could have been the possible error in the radius, and we knew our ideal radius was 6, couldn't we think, well, what if it was perfect? Like, what would the volume be if it was exactly 6, right? We could figure out V if the radius was exactly 6. You think, but if the radius was up as high as 6.01, couldn't we plug that in, get the volume, and then just subtract those two and get this answer? We could do that, but it turns out that is more work than what we just did. Taking, obviously we're learning derivatives, so that takes time to think through. Maybe you could get that something like that right away. How is plugging in numbers, not faster than this calculus that we're just learning? Even so, and even if you start thinking about technology, doing differentials like this is actually quite a bit faster than plugging two numbers in to something like that and subtracting them. So once we take the differential of both sides, boom, boom, now we have it. And that is really, really accurate. The truth is, this is not the exact, okay. Ooh, where am I going here? No, it is the exact, because doing all of this, that's the little bit of change that the volume would experience. Okay, I take that back. No, that's perfect. That is exactly the maximum error in the volume right there. Okay, I better stop talking and end this one before I say anything else.